Hi, when we want to produce a PWM signal for an inverter, the common practice is that we take the reference signal. So for example, here I have a half sine wave as the reference signal. After that, we need to take a carrier signal. This carrier signal, usually we take it a sawtooth or a triangular waveform. So let me take a triangular carrier signal. Then we compare the reference signal with the carrier signal. Whenever the reference signal is larger than the carrier, for example, in this region, and then the PWM will be on, and whenever the carrier signal is larger than the reference signal, PWM will be off. So in this region it will be on, and then after that will be off. Basically, by this way we produce the PWM signal. Now the question is that why do we always use triangular or sawtooth as the carrier signal? Why can't we use other type of waveform as the carrier signal? So for example, here I want to use a sine wave which is shifted upward as the carrier signal, and I can do the comparison again similarly as I explained before. So this would be the PWM signal that I produce with the sine wave carrier signal. Now the question is why this PWM is no good, but the other PWMs produced by carrier signal of sawtooth or triangular, they are considered to be good PWM. Now in this video I'm going to answer this question. Okay, so to answer this question, we have to first understand what kind of criteria do we use to say that a PWM signal is good. So let me draw the PWM signal with the triangular one. Okay. Now the criteria that we have is that if we take any part of the signal, so for example this part, any sections of the signal, and we calculate the integral of that section. So let me I show you. So for example, here I took this part of the signal and I calculate the integral of that section, the blue part. So this integral should be equal to the integral of the PWM signal over this region. Now obviously in this case they are not equal, even though we use triangular waveform as the carrier signal, but the reason is because the frequency of the carrier signal is not very high. So if I increase the frequency of the carrier signal, you notice that so here I have a higher frequency, and if I plot the PWM, we notice that, for example, this integral, the blue region, would be more or less similar to the integral of the PWM signal, because PWM has some extra region on this section and also on this section, but instead it doesn't have the middle part. And actually, if we increase the frequency of the PWM even more, then these two integral, the blue and integral of the PWM, will be exactly similar. So this condition is true for sawtooth and triangular waveform, but it is not true for other waveform, for example, for a sine wave. Now, first thing that I'm going to do is that I will show you that this integral will be always equal when we use sawtooth and triangular. And then I will show you that it is not true when we use, for example, a sine wave as a carrier signal. Okay, so before I show you the proof, I should mention that if I remove these parts. There is something very important that I have to show. Now consider this reference signal and assume that we take a very tiny time steps here, like a very small delta t. Now obviously during this small delta t, the magnitude of signal cannot change. Wherever we are, if we are here or we are here, the magnitude of signal cannot change a lot because the time delta t is very small. Now let me, for example, I take this small delta t, and if I take really small delta t, what you notice is that the signal will look like a flat line. So basically what I have to prove is that if I have a flat line above, let's say, like at certain magnitude, and if I use a triangular waveform or a sawtooth waveform, then the condition of the integral that I mentioned is true, because every main signal we can actually convert it to small delta steps, delta t steps, and then basically we put them next to each other and build the whole signal. So the proof that I'm going to show you is only for when the time step is very small and this signal is more or less flat. All right, so now let's see how to prove this. All right, so in order to prove this, we need to use the software, the favorite software, Paint. So let's say this is y is equal to 0. And then we have the signal, which is here. And now we have a triangular waveform, which, let's say this triangular waveform, it starts from here and then it covers, basically this piece of the signal covers one full cycle. All right. So what I have to show is that, so the PWM that is produced here is basically this signal. So it would be something like this one. And also something like this one. Of course, these are symmetric. I draw them a little bit bad. But what we have to show is that the area underneath this black one is equal to the area underneath these two sections. Now we can actually simplify this one because I don't need to show for both sides because these are equal. So I can divide this into half. And basically I will show that the area of this region, the yellow one, is equal to the area of the orange one. And actually, if you look only at the half of this is a sawtooth waveform. So by this, first I prove for the sawtooth, and then we can make it double. Then we have also for a triangular waveform. So these two are actually the same thing. Now the task is to prove that yellow, the area of the yellow region is equal to the area of the orange region, because the area of here, they are the same in both cases. So I name these things. For example, here is A, this is B, this is C, this is D, and this is F. Now this is basic geometry actually. So we have two right triangle base. So this is first one, if you look at here, and this is the second one. And these two triangle, because these angle are against each other, so they are equal. So basically triangle ABC is actually similar to triangle DFC. So these triangles are similar. If they are similar, we can write the ratios. Basically, the ratio of AC to DC is equal to the ratio of AB to DF. And we can do the multiplication. So what we conclude is that AC times DF is equal AB times DC. Now, what is AC times DF? Let us look at here. So this is AC, and DF is basically this part. So AC multiplied DF, this is the orange area. And AB is actually this little part, which is equal to also this little part, because they are all similar. And then CD is this side. So this is equal the area of the rectangle, the yellow rectangle. So this is the yellow. So basically, by this simple geometry, I have shown you that for a sawtooth, the area of underneath this PWM is equal to the area underneath the signal. And we can make it double. Basically, the area underneath the signal is equal also for the triangular one would be the same. The PWM produced by the triangular would have also the same area. So we can see that this condition is fulfilled. And remember that I didn't consider anything related to the height of this signal. So this signal, whatever that height is and whatever the height of the carrier signal is, these equations are correct. So now if I have a main signal, which is basically something like this, let's say, and let's say here I have the carrier signal, which color should I use? Maybe black, or maybe another color, red. So if I have the carrier signal, which is something like this, and like with higher frequency, but I cannot draw now, then it doesn't matter actually at which part of the signal we are, because here we did not consider the height of the triangular waveform and the magnitude of the signal. This doesn't matter. So the PWM that we produce, the area of the underneath PWM signal will be equal to the area underneath the signal. Of course, the frequency of the carrier has to be high. Now, this condition will not be true if we use a sine wave as the carrier signal. So let me see if I can show that one. Okay, so now for the sine wave, this is a shifted basically sine wave. I have wrote already the equation to save some time. Again, we can divide it into two parts. So we have to show that the area underneath this blue one is equal to the area underneath the signal. Now the height of the signal, I consider it as HS, and the height of the carrier is HC. I consider the shifted time. So here is t prime 0. This is one full cycle, and this is where they intersect. Basically, the equation of this carrier signal here is this equation, hc divided by 2 times 1 minus cosine 2 pi t prime divided by tc. Now here we can see that the area of the blue region is basically the height hc multiplied this tk. And the area of the black part, only half of it of course, is hs, the height of the signal, multiplied tc divided by 2. So now these are the areas. Of course I can calculate tk from here, because I know that tk is at this region. So this sine wave, the magnitude should be equal to hs when the time is tk. So I can put tk in that equation basically and equal to hs after some simplification. So this is basically the tk. So now if I put this one into the area, so a blue basically would be hc multiplied tc divided by 2 pi times cosine minus 1 minus 2 hs divided by hc. And this one is obviously not equal, it's obviously always is not equal to this area, because you can simplify this to tc divided by 2, and hs, the height of the signal, would only maybe at one point would be equal to this other equation. It will not be always true that, so if we have a complicated signal like going up and down, and let's say this is the reference, and we use the sine wave as the carrier signal, then at some regions maybe this integral will be equal, but at some regions these two integrals are not equal. It depends on the height of the signal and height of the carrier signal. So that's why we do not use, let's say, a sine wave as the carrier signal, but we use triangular and sawtooth. Now I'm going to show you this a little bit more visual in MATLAB Simulink, and then you will understand it a little bit better. Okay, so here I have a half bridge configuration. This is the voltage source, this is a half bridge, and here is the load. But actually this part is not important right now. The part that is important is the control signal, which sends the signal to the gate. Here I have a sine wave, which I take the absolute value, so it's actually half sine wave, like only the positive part. And then once I use a triangular signal as the carrier signal, so the frequency of the signal here is 500 Hertz. And basically we compare them. Whenever the signal is larger than carrier, it will be on, and whenever it's not, it's off. Now in this part, actually I am going to integrate the signal from beginning till any point. And on this line, I will take the integral of the PWM signal. So let's see what do we get. So basically here is the signals. This is the input. And this is the triangular waveform, and the orange one is the PWM produced. And if I look at this oscilloscope, then what we see is that basically the yellow one is the integral of that input. It's the cumulative integral, and the blue one is the cumulative integral of the PWM signal. Now, of course, they are not very much matched, but they are very close. If I increase the frequency of the PWM, let's say, of the carrier signal, let's say for example 5000 Hertz. So now this will be the PWM, and if you look at the integral, you see that they are on top of each other. And if we even increase more, then they will be exactly on top of each other. Okay, so this is when we use a triangular waveform as the carrier signal. So what will happen if I use a sine wave as a carrier signal? So this is a shifted sine wave. Basically, now I set it, this is a sine. I set the frequency to 500 Hertz. Let's run it. So this is basically the shifted sine wave, and that will be the PWM produced. And if you look at the integral, so this is the integral. And now if I increase the frequency, let's say I go to 5000 Hertz. So this is now the PWM produced, and this is the integral of the signal. So it becomes closer, but it's not really good because we are already in 5000 Hertz. And if I even increase it to more, let's say I go to 500 kilohertz, very high frequency. That will be the PWM signal produced with a lot of pulses. And if we look at the integral, you see that these two integrals are not equal. So at this region, for example, the PWM integral is less and this region is higher, and there is one point that they are equal. But when we use a triangular or sawtooth, these two integrals will be exactly the same as you have seen before. All right, so I want to end this video here. Have a good time. Bye.